Okay, all right, let's get started. So, this is the last seminar of the semester. It's now week 12. So, let's do something a little bit different. Let's not do too many problems this week, but we'll kind of cover a little bit more on the theory side. Okay, so last week we looked at divide and conquer algorithms like binary search, merge sort, and we also looked at more difficult divide and conquer problems. So we looked at more difficult divide and conquer problems. And today is going to be a bit different in that we'll try and see divide and conquer from a slightly different perspective. So what I'm going to do is I'm going to write a divide and conquer algorithm, but a very generic divide and conquer algorithm. Okay, here's what I'm going to write. So let's define a function, divide and conquer on some space S. And the idea is if the length of S is 1, then we just return, or return the result of S. Then if we don't have something of length 1, or if the size of the problem is not 1, then we divide it, we let L and R be divide on S. This is some function where we split it into the left and the right. Then we do A is divide and conquer L. B is divide and conquer R. And then we do some sort of combine step. So we return combine A, B. Okay? So this is the underlying structure of divide and conquer algorithms. And it's not only easy to understand, but it's also very useful. So what I want you to do is to understand this structure and show how it's kind of used in a lot of applications. So when we think about this function, what we're doing is we have some problem like this, S, and we divide it into two subproblems. Let's say this is L, let's say this is R. And we keep doing this. Let me put my paper up. There we go, there's L and R. And we keep subdividing L and R like this. So let's call this LL, LR, RL, RR. And we keep subdividing until we get to size 1, and so forth. And then we combine these solutions to get up to the top and the solution for the original problem. All right? Now, what this looks like is kind of like a tree sort of structure, right? So let me introduce you to the tree. So the tree is the close relative of the graph. So let me talk about trees. So trees are a close relative of graphs. They are a type of, they're essentially a type of acyclic graph. And they have a special structure where every node has at most one parent. I'll say that they're also directed. Yeah, in some sense they are directed in that there's a direction for a parent and a child and so forth. Okay? So yeah, we have this structure called a tree. Okay? And trees look kind of like this, right? They look like this. Maybe you have, let's say I have three things here. This is like what we call a root or the parent, or yeah, we call it the root because it's like the head of the tree. Okay, and maybe this one has, say, two children, this one has one child, this thing has, I don't know, four. But the important thing to note is that there's a kind of hierarchical structure here. Okay, so each node, for example, this node, only has one parent, and that's this. Like this is its ancestor. So I can't do something like this. So this is not a tree, right? Whereas this is a tree, this is a tree, and so forth. Even this is also a tree too. Okay, these are all trees. Okay, so let's try and understand this from a slightly more real-world perspective. Okay, so the real-world perspective on this is that trees are used to represent hierarchical structures. Okay, let me write that up. Hierarchical structures. And the most famous of these is essentially your family tree, which looks kind of similar to this in that you have children at the bottom, parents at the top, and you kind of map out the entire line of your ancestors and descendants that way. Okay, that's one application of a tree. Another application of a tree might be company organization. So for example, we might have our CEO at the top. Okay, and the CEO has certain subordinates, but it does not have a boss. The CEO does not have a boss, right? So it is the root of the tree. The CEO has some number of subordinates, they have some number of subordinates, and so on, until you get to what are called the leaves of the tree, right? Whereby these leaves do not have any subordinates. Does that make sense? Okay, so these are some applications of trees. Trees are used to model all sorts of hierarchical structures, but they're also used heavily in computer science, and they're very similar to the types of structures, or they are the types of structures that arise from divide and conquer algorithms. Okay, so there are a lot of ways that we can kind of define trees. So one way, let's kind of look at, let's look a little bit at the formal representation. So one way we can represent it is as a collection of nodes. So formally, right? A tree is a collection of nodes where each node is a structure, right, that contains its value, and two, a list of children. Right? And we note that no reference is going to be duplicated here, and that nothing will point to the root. All right. So that's one way to define a tree. Another way of defining a tree is essentially like using kind of the directed acyclic graph kind of notation. So one way is, we can also say it's a directed acyclic graph where every node has one parent. That's usually good enough to define a tree. Okay? All right, so now let's look at kind of how the trees are kind of defined and derived from divide and conquer algorithms. So let's look at that. Let's get some more paper. Okay, so let's go back to divide and conquer algorithms. And I'm going to introduce this structure called a binary search tree. Binary search tree. And the whole idea of the binary search tree is that it's an extension of a binary tree, which is essentially a type of tree where every node has exactly two children, something like, or 2 children or less. So for example, this is a binary tree because every node, so this node 1 say, has 2 children, let's say that 2 and 3, 2 has 2 children, that there are 4 and 5, and 3 has less than 2 children, which is 6 in this case. All right. So every node has 2 children or less. That's why it's called a binary tree. Now, a binary search tree is an extension of this where node A is to the left of B of node B if the value of node A is less than the value of B. Okay, let's say it's less than or equal to. Actually, let's assume that we have unique nodes, so less than, unique values in this case. Node A is to the left of node B if the value of A is less than the value of B. Node A is to the right of node B of node B if the value of A is bigger than the value of B. All right, so let's do an illustration of this. Let's say I had a node and it had a value of, say, 3. Then a node with a value of, say, 1 would be to the left of it, right? And now let's say I wanted to insert the node 2 into this thing. So what would happen is that 2 is less than 3, but it's bigger than 1, so it goes to the right of 1, whereas 0 would go to the left of 1. Right? And if I wanted to insert, first of all, maybe 5, it would go this way, and 4 would go to the left of 5. I hope that makes sense. So the idea is that when I insert, all I'm doing is I'm going to the right if it's bigger than something, and I'm going to the left if it's smaller. So if I wanted to insert a node, say, let's say, I don't know, 3.5, okay? 3.5 is bigger than 3, it's less than 5, it's less than 4, so it would go here. Okay? Does that make sense? I hope it does. Anyway, so how does this all connect to binary search? Which is kind of This is kind of a detour, isn't it? So, yeah. So consider the problem of finding an element in a binary search tree. The idea is that, let's say I want to find node 3.5, okay? Let's say I want to find node 3.5. How do I find this node? I don't have to search every single node. I mean, one way to do it will be, I'll search this node, this node, this node, this node, this one, and then we get here and we find it, okay? But that's really inefficient. We can actually use the fact that this is organized in a nice way by simply going right whenever we find something that's bigger and going left when we find something that's smaller. And when we think about it, that's the essence of binary search. So what binary search is, so the classical binary search is searching for an element in a sorted array, right? All it's doing is treating the array as if it is a binary search tree, right? It's treating it as if it's a binary search tree where the root is in the middle, right? Which, in this case, sorted arrays are a lot like binary search trees. But binary search trees have more special properties, and we're going to see that in a moment. So now let's talk about merge sort. So let's talk about merge sort. Okay. So let's say I have my tree like this. 3, to the left of it is 1, to the right of it is 2, to the left of it is 0, 5, 4, let's say there's 3.5 over here. Okay. So I have this thing, and let's say I want to visit these in a particular order. I'm going to call this an in-order traversal of a tree. And you might notice that I've used the word traversal just like I used it with graphs. And that's no coincidence. A tree is just a specific type of graph. Okay? So we could traverse this by using breadth first search or depth first search, something like that, right? But we're going to do it in a specific way. We're going to do a kind of depth first search in a specific way. The way we're going to do it is the following. What we're going to do is, our algorithm is the following. Define an order of the tree, right? Let's have a node here. And the algorithm is this. First, we call in order on the tree and the left of node. Then we visit the node, and then we call in order on the tree and the right of the node. Okay, so what do I mean by this? All right. So let's say I have my tree, which is here. So first, I have 3, but I call in order on the left of 3, which is 1. So what I'll do is I'll visit the left subtree of 1, which is 0. Then 0 doesn't have a left subtree. So what I'm going to do is I'm going to write it down, which is the second step, visit the node. And it doesn't have a right subtree. So now we backtrack, okay? So for 1, we already visited its left subtree, but we haven't visited the node yet, so we write down 1. Now we can visit the right subtree, and it does have a right subtree. So we have 2. 2 does not have a left subtree, it only has itself, and it does not have a right subtree. So we go back, but with 1, we've already visited the left subtree, we've written down the node, we've written down the right subtree, So we can simply backtrack even further to 3. And, well, now we've visited the entire left subtree of 3. So we write it down. And now we visit the right subtree of 3. And then we visit the left subtree of 5, the left subtree of 4, and we get to 3.5, and so forth, right? We go back. It does not have a left or a right. We write it down. We go back. Now we write down 4. It doesn't have a right subtree. We write down 5. It doesn't have a right subtree, and we are done. So what we can notice here is that by doing an in-order traversal of a binary search tree, let's call it a BST from now on, we obtain a sorted array. Okay, so what are we doing when we do merge sort? Well, what's actually happening is that we're actually just inserting everything into a binary search tree and then traversing it. So for example, when we have an unsorted array, let's say 2, 0, 1, 3.5, 4, 5, 3. Okay? What we're actually doing is we're basically inserting all of these things into a binary search tree, and then we're going to traverse that tree. So we'll insert 2, then we'll insert 0 because it's to the left, we'll insert 1 to the right, we'll insert 3.5 to the left, 4 to its right, 5 to that node's right, and 3 to the left of 3.5. And then we will do the in-order traversal of that tree, and we will get our answer. So let me do that. And note that this in-order traversal takes O of n time. O of n time. Because we're simply going through all nodes. Through all nodes in a particular way. And we never repeat. Okay, so let me go through that in order traversal of our sorted array. So our sorted array was 2, 0, 1, 3.5, 4, 5, and 3. So what we're going to do is we're first going to put everything in a binary search tree. So we have 2 first. 0 is to the left of 2. 1 is to the right of 0. 3.5 is to the right of 2. 4 is to the right of 3.5. 4. 5 is to the right of 4. And 3 is to the right, it's to the left of 3.5. Yeah, it's bigger than 2 and less than 3.5. Okay, we have this kind of slightly wonky tree. I'll address the fact that it's wonky in a little while. But it's a tree nonetheless. And when we do our in-order traversal of this tree, we will get, in fact, what we want, right? So we have 2, we go to its left subtree. 0, we try its left subtree, it doesn't have one, so we write it down, right? Then we go to its right subtree, 1. 1 does not have a left subtree. We write it down. It doesn't have a right subtree. Now we backtrack. We've covered 0. We backtrack. We go to 2. Now we've covered the left subtree of 2, so we write it down. We go to the right subtree. Now 3.5, we go to its left subtree, right? Because we got to a node, we go to its left subtree first. 3 does not have a left subtree, so we write it down. It doesn't have a right subtree, so we go up. 3.5, we write it down because we visited its left subtree. Then we go all the way to 4. We write it down because it doesn't have a left subtree, and we write down 5 because it doesn't have a left subtree. So we notice that what merge sort is, we can write it in the following way. Insert each node into the binary search tree T. That's step 1. So for each node we insert, obviously I'll just write for each node. We insert that node into the binary search tree, and we use the comparisons to figure out where to insert. Okay, and step 2 is perform the in-order traversal of T, and that gives us the sorted array. Now, my question is, how long does the alternate version of merge sort take? It seems like this is just the same as the original, except somehow we are manipulating it using a structure rather than using a traditional divide and conquer algorithm. But how do we show that the structure version with the trees and the normal divide and conquer version take the same amount of time? How do we do that? So there are 2 steps here. The first one is the insertions, right? And the second one is the in-order traversal, which we know takes O of n time. It's pretty obvious because all we have to do is just go through every single node in the right way. The question is the insertion really, does it really take the right amount of time? So we have n nodes to insert. Okay? We have n nodes to insert, and well, how long does each insertion take? Now, this is a good question. I mean, and the answer is very interesting. The answer is if the tree is decently balanced, it takes O of log n time. Okay? But if it is not balanced, it could take O of n. All right, so let me explain what being balanced and not balanced means. So, what I mean by balanced is something where balanced BST. Okay, what I mean by this is the tree is kind of evenly spread out. So something like this. This would be balanced. Okay, informally, this is what it means, right? Whereas something like this, all right, is not balanced. Why is this not balanced? Well, first of all, it's completely skewed to one side, right? It's not nice and even. But what I mean is that it's going to take a very long time to do an insertion. So let's say I have the values are 3, 4, 5, 6, 7, and I want to insert 8. insert 8. Okay. If I had a nice structure like this, right, whereby, okay, this doesn't have 5 nodes, but if I had some 5-node tree like this, 1, 2, 3. Okay, so let's say I put 5 here, then I put 6 here, I put 7 here, and I put 4 here, and I put 3 here. Okay? So this would be a nice way that if I had to insert 8, it wouldn't take too long, right? Something like this wouldn't take that long, right? Because I only have to go through 2 comparisons to get there. So this would be decently balanced. So this would mean O log n insertion. Okay? But if the tree is totally skewed, I have to compare to 3, I have to compare to 4, to 5, to 6, to 7. Okay? And that takes, let's put another node here with 8, when I insert 8, that takes O of n time. So now you might observe something, right? Which is that it matters what is at the root. Right? So the root matters. I'll write it this way. What is at the root matters? A lot, actually. Right? And it determines the runtime for the insertion. Okay, so the question is, if the tree is decently balanced, insertion takes, for one node, takes O of log n time. Why? Because there are exactly log n levels for a tree with n nodes, right? Can you see why? Because, so let's say there's 1 node here, 2 nodes here, approximately 4 nodes here, and so forth, right? So let's say there's 1 plus 2 plus, let's say I draw a node here, plus 4 equals 7 equals 2 to the 3 minus 1 nodes in the entire tree, but there are only 3 levels. 3 levels, right? Which is log 2 of nodes plus 1, okay? So doing that binary search and then just putting the node in the right place takes log n time for the binary search, or log n time for the sequence of comparisons that gets you to the end, to the leaves, and then simply O of 1 time for the insertion if you implement this tree as a linked structure, okay? But if the tree, so inserting n nodes, n nodes takes O(n) log n. So the total running time of the alternate version of merge sort is just O of n log n plus O of n for the in-order traversal. This is traversal. This is insertion of n nodes. Insertion of n nodes. And this is just O of n log n, because n log n is bigger than n. So the alternate version of merge sort takes exactly the same time as the regular version of merge sort, as long as the tree is decently balanced. So the million-dollar question is, how do we keep the tree balanced? So how do we keep the tree balanced? Now the idea is that if we rotate or rebalance the tree after every insertion by rotating the tree, so we rotate the nodes and move the nodes up in order to change the root node every time before we insert, while not disrupting the binary search property, then we were able to keep the tree balanced. So the idea is we rotate the nodes of the tree, careful to preserve, or careful to preserve the binary search property, which is that everything to the left is everything that's less is to the left, everything that's greater is to the right. I hope that makes sense. So I'm not going to really describe how this rotation procedure works. It's quite complicated, and it's in an advanced class on data structures. But I will highlight the fact that this allows the rotation allows for insertion, search, and even removal in O log n time for a single node. For a single node, okay? And this data structure is called a balanced binary search tree. So it does search, insertions, and removals in O of log m time for each node. And the point is that if we do the alternate version of merge sort with a balanced binary search tree, we are guaranteed the O of n log n running time. Okay, so why should we care about this? What are the applications? So let me highlight what the applications are quickly. The big application is inserting into a sorted array. Okay, let me explain why this is a big problem. So imagine I have an array like this, say 1, 2, 4, 5, 6, 7, and I need to insert 3. Insert 3. Okay? So I can be clever about this and say I can use binary search to find the place I can insert this. I do the midpoint, I do another midpoint, I get here, and I say, okay, I need to insert 3 right here. Insert 3. The problem is that even if you can search for the place to insert in O of log n time, well, the insertion is going to take a longer time because you have to adjust all of the other elements forward. You have to adjust the 4, 5, 6, and 7 forward, and then plop the 3 in. And that takes O(n) time. So the search equals O of log n time, and the insert is O of n time, so total O of n. Make sense? So you doing it with a sorted array would be bad, because it would take linear time. What if we use some sort of linked structure? So for example, we have something like a structure where we have some pointers like let's do 1, it's pointed to 2, it's pointed to 3, not 3, it's pointed to 4, it's pointed to 5, which is pointed to 6, which is pointed to 7. Okay? So we have 1 is pointed to 4, which is pointed to 5. 1 is pointed to 2, which is pointed to 4, which is pointed to 5, which is pointed to 6, which is pointed to 7. All right, and I want to insert 3. Now, assume we know that 3 should go here, right? So assume we know 3 should go after 2. Right? Let's assume we know that 3 should be inserted in this particular spot. All right? We could have changed the numbers so we might not have known that a priori, okay, beforehand. So assume we know that, then all we have to do is adjust our pointers. So we could just do this. We could have 1, 2, and then 2 points to 3, and 3 points to 4, like this. We just adjust the structure slightly, and we just keep on going. 5, 6, 7. Right? We could just adjust the structure like this and keep going. The problem is, how do we know? So with the sorted array, we knew where to insert it, but the insertion took ages. With the linked structure, the insertion is quick. It's quick and easy. We just adjust 2 pointers, right? We just make 2 point to 3, make 3 point to 4. But we don't know where to put the 3. And we can't do binary search on this linked structure. Why is that? Right? Because it's absolutely pointless, because we have no idea where the midpoint is. We only have references to all of this sort of thing. Okay? So what we need is a cross. So the balanced binary search tree. The balanced binary search tree is a cross between a sorted array and a linked structure. Okay, it's a cross between the array, the contiguous structure of the array that gives you midpoints, and the linked structure that allows you to insert fast, right? So they give you certain things. This gives you binary search, and this gives you fast insertion. And the binary search tree combines all of this in order to do search, insertion, and removal in O of log n time. It's actually kind of a miracle. And a lot of applications in the modern world, certainly in the tech industry, making things work at scale, require being able to insert into some sort of structure that is already sorted. Think databases, right? Let's say some database has a particular ordering by certain key, and you want to maintain that order, but you also want to insert something so that the order is preserved. How do you do that? It all comes down to types of trees. There are many different types of balanced binary search trees, but one of them, so there are different types. For example, the 2-3 tree, the red-black tree. I'll leave this for you to look up. Display tree, and so forth. Yeah, there are many more. The B tree, not the B tree. Yeah, these are some of the different types. Yeah. Oh, AA is another one. AA tree. This is another one. There's a nice implementation in Python of an AA tree in the book Python Algorithms. I encourage you to look that up and implement it yourself and play with it. But yeah, that kind of concludes what we want to do. So I showed you that all divide and conquer algorithms have this particular tree structure that lies at the heart of the algorithm itself. And that lots of divide and conquer algorithms like binary search and merge sort can be interpreted as algorithms on these tree-like structures. Right? Binary search is simply searching through a binary search tree. Merge sort is insertion into a binary search tree followed by a traversal of it. Right? Things like that. So there is a correspondence between divide and conquer algorithms and trees, and sometimes it helps to look at things one way, and sometimes it helps to look at things the other way. And these balanced binary search trees have enormous application. They lie at the heart of computer science, and they're very, very useful because they combine the aspects of a sorted array and a linked structure. And for example, in Java, you can find this as the tree map and tree set. Okay, in Python, you can easily do it yourself in like less than 50 lines of code. We don't really have time, but like there is a reference implementation in the particular book I referenced, Python algorithms. So I encourage you to look at that and implement it yourself. All right, that concludes all of the seminars for this semester anyway. Hopefully we may be back next semester to do some more interesting things and definitely some more programming. See you around.